All right, ladies and gents, today we will be discussing conjugate acid-base pairs within an equilibrium, acid-base equilibrium. On the left-hand side of your equation, you will have the normal naming that we have used thus far, acids and bases. As we learned last class in the previous lecture, we're going to focus on the Bronsted-Lowry definitions, hydrogen ion donors and hydrogen ion acceptors. As we look from the reactant side to the product side, the NH3, the ammonia molecule, is gaining a hydrogen ion from the water molecule. So we would define that as our base. At the same time, going from the reactant to the product side, the water molecule is losing a hydrogen ion. So we would define that, according to Bronsted-Lowry, as our acid. Now, the conjugate acid-base pair show up on the product side, and those refer to the reverse rate of reaction. So if we look at the reaction in the reverse direction, now we are going from NH4 back to NH3 in the reverse reaction rate. The NH4 is losing the hydrogen, so we would then define that as the conjugate acid. Likewise, the OH in the reverse direction is gaining a hydrogen, so we would define that as the conjugate base. Conjugate acids and conjugate bases are only used on the product side of an chemical equilibrium and always refer to what is happening with the acid and base in the reverse rate of reaction. Moving on, the next topic that we have to discuss is the definition of a particular type of species called amphoteric species. Amphoteric species can be those that act as an acid or a base. They won't act as an acid or a base in the same reaction, but depending on what they are reacting with, they can behave either as an acid or as a base. If we look at the first reaction listed here in purple, the bicarbonate ion, the HCO3 1-, going from the reactant side to the product side, is gaining a hydrogen. So therefore, we would define that as our base. Likewise, the hydrogen chloride, or also known as hydrochloric acid, from reactant to product side is losing a hydrogen. So we would define that, no surprise here, as an acid. If we then look at the second reaction listed in purple, the HCO3, now moving in that from left to right, from reactant to product side, is now losing a hydrogen ion. So according to our Bronsted-Lowry definition, that would then be defined as an acid in the second reaction. The NaOH would be defined as our base. Therefore, we define HCO3, the bicarbonate ion, as an amphoteric species, a species that can behave as an acid or as a base, depending on the chemical reaction that it is participating in. The most common amphoteric species that we will use in class is water. You will hear us refer to water often and a lot as an amphoteric species. The final concept that we have for this lecture today is to look at what's called the autoionization of water. The autoionization of water happens in most water samples to a very, very small degree. You will have two water molecules that will come into close contact with one another within your water sample, and one of the protons, one of the hydrogen ions, will be transferred from one water molecule to another. This happens for a fraction of a second, and then it reverts back to two water molecules. But for a very, very short period of time, you have an H3O positive ion in your solution and an OH negative ion in your solution. That H3O positive we haven't used up to this point in class. That is called the hydronium ion, and we form a hydroxide ion as well. Now, oftentimes, instead of referring to H3O positive and OH, we'll simplify this reaction sometimes and just show one water molecule that then establishes an equilibrium between a hydrogen ion and a hydroxide. You hopefully can see the similarities between the equation that's listed up top here and the equation that's listed down below here. All we've done really is remove one water molecule, this water molecule right here, and simplified the hydronium ion down to just be a hydrogen ion. Now, if I were to write an equilibrium expression for the second reaction listed here, we would have our K equals the hydrogen ion concentration times the hydroxide ion concentration. We don't include, again, the water because the water is in the liquid state and that concentration does not effectively change when we add or remove water from our system. This is a special K expression. This is the autoionization of water, so we call this KW for this expression. KW refers to just the autoionization of water, and it is specific to 25 degrees Celsius. Now, when water is neutral, the hydrogen ion concentration has to equal the hydroxide ion concentration, and both of those values are 1.0 times 10 to the minus 7th molar. So, what we end up with is our KW expression. We have the hydrogen ion concentration times the hydroxide ion concentration. Since they're both the same concentration, we basically square that concentration and we get 1.0 times 10 to the minus 14th. That is your KW value at 25 degrees Celsius, and that is a constant at 25 degrees Celsius. This equation gives us a lot of flexibility. We now have the ability, if we know the hydrogen ion concentration, we can solve for the hydroxide ion concentration or vice versa, knowing that KW 1.0 times 10 to the minus 14th will stay the same as long as the temperature stays the same. So let's do a quick practice problem with this. If I go ahead and we scroll down here. Let's say we had a hydrogen ion concentration of 2.3 times 10 to the minus 3rd molar. We could use our KW expression, which is the hydrogen ion concentration times the hydroxide ion concentration, knowing that we're at 25 degrees Celsius. Our K value is a constant. We have 2.3 times 10 to the minus 3rd molar as our hydrogen ion concentration, and we can go ahead and solve this for our hydroxide ion concentration. So go ahead, divide both sides by 2.3 times 10 to the minus 3rd. This side cancels out, which means we're left with just OH over here, and we go ahead and solve for the other. And I get 4.3 times 10 to the minus 12th molar as my hydroxide ion concentration. Now, the two statements that are at the top of the smartboard right here give us an indication as to whether or not we have an acidic or basic solution. Since our hydrogen ion concentration is 10 to the negative 3rd, and our hydroxide ion concentration is 10 to the negative 12th, the hydrogen ion concentration is clearly greater than the hydroxide ion concentration. So we would fall into this scenario given these two concentrations because of how many orders of magnitude the hydrogen ion concentration is greater. It gives you an indication of whether or not you're dealing with an acidic or a basic solution.